Welcome back to physics. Today we're going to deal with applications dealing with refraction and lenses, specifically the human eye and how you see. So I've got two diagrams over there to the side. Top one, kind of an overview. The bottom one, some of the more specific parts. We're not going to focus on all the biology. Rather, we're going to focus on the parts of the eye that are relevant to the refraction and to how you see. So the pupil and the iris. Pupil, it's not a thing, it's a hole. It is a hole in the iris, and the iris is the colored part of your eye that surrounds the pupil. The pupil being a hole, that's where light goes through. So that is how light enters your eye to be able to form an image. Your iris then, the colored part, will control the size of the pupil. When it's dark outside, then the iris will spread and allow the pupil, the hole, to become larger and allow more light in. When it's very bright outside, then the iris will close in and make the pupil smaller so that not too much light gets into the eye. Next two parts, the lens and the cornea. Lens and the cornea on the diagram below, and I'm going to highlight a little bit. Your cornea is overall this entire part of the eye, and then the lens would be that part that I'm highlighting right now. Your lens and cornea both have properties to be able to refract the light. If you look at the shape of the cornea and you look at the shape of the lens, they are both in the shape of a converging lens. So both of them serve as or take on the role as a converging lens. They both refract the light. The cornea does actually most of the refracting of the light. In other words, it gets the light traveling in approximately the right direction for you to be able to see. Then the lens does more of the fine focusing of the light to be able to get a clear, crisp image that forms on the retina at the back of the eye. Both parts are needed. Both parts have separate roles. If your cornea is not working correctly, you can't see clearly. If your lens is not working correctly, you cannot see clearly. I'm going to pop over to another slide, talk about an application of that, and then come right back here. Pondering physics. Maybe this summer, we'll have to see when all this gets over with. You are at the swimming pool. So here is the pool. Here you are outside of the pool, ready to get in the water, and a few moments later, here you are in the water, underneath water. Now, when you are underneath the water and you open your eyes, how do things look? Well, if you don't have goggles on, it probably looks very blurry underwater. You get a refraction because there's a difference in substances. So let's think about the substances. When you're up here in air, then the boundary is air to cornea. Air has an index of refraction of 1.000293. Cornea has an index of refraction of 1.376. And that is a significant change in index of refraction. And so then by that change, the light can be bent. When you're underneath water, then the boundary is water into cornea. Water has an index of refraction of 1.333, and that's from our table. Cornea has an index of refraction of 1.376. Those are almost the same, and because they're almost the same, you can't bend the light with your cornea, and if you can't bend the light, you can't see clearly, and so everything is blurry underwater because basically your cornea, it can't bend the light, because there is not enough difference in the index of refraction. So then how do you cure that problem? You put goggles on, swim goggles. And what do swim goggles do? They trap a layer of air against your eye So then it's a plastic coating, the goggles are, and then you have a layer of air, and then your eye or your cornea. So then you have a boundary of air to cornea, and then your eye can function normally. Your cornea can refract the light. So when you wear goggles, it's not about the design, the plastic, or anything about that. It's about trapping an air bubble against your eye to allow the cornea to do what it is supposed to do. So back to here, your cornea does that major refraction. The lens then just does the minor refraction, gets the fine focusing of the image to form on the retina. Your retina, that is the yellow along the back of the eye, and I'm going to try to highlight. We'll highlight in green here along the edge. This right next to the green line that I'm putting all the way around here, that is your retina, just to the right side or above or below that green line that I put. The retina is basically where the light focuses to be able to form an image. Your retina is where you have rods and cones, and these rods and cones convert the light into an electrical signal, and then this electrical signal is carried to your brain by the optic nerve. So your eye does not see. Your eye refracts the light then focuses on the retina then converts the light into an electrical impulse that then goes down the optic nerve to the brain, and then your brain gets this signal and has to make sense of it. When it makes sense of it, then you see. So then sight occurs in the brain. The eye is only the thing that is receiving the light, receiving the signal. Just like hearing does not occur in your ears. Your ears receive the sound waves, convert it into an electrical wave, which goes to your brain, and your brain then interprets it. Hearing occurs in the brain. Now, one other thing I wanted to hit here, and that is your ciliary muscles. And your ciliary muscles are basically above and below the lens, and they will stretch and they will change the shape of the lens. Ciliary muscles connected to the lens, pull, push on that lens to be able to change its shape. In changing the shape of the lens, they allow you to focus on things that are near and far away. You can look at something in front of you. You can look across the room at something more distant, and the ciliary muscles are working to change the shape of the lens to be able to change the focal length of the lens so that that image can still come into focus clearly. Now, you're all very young. Your ciliary muscles are working pretty well. When you get into your 40s, those ciliary muscles start to atrophy. They no longer work as well. The lens loses some of its elasticity. The combination of that is you can't change the shape of your lens as easily. You are most using your ciliary muscles when you are looking at something close. So if you are watching lots of videos, reading lots of books, your eyes get tired when you are looking at something close. When you hit your early 40s, then those ciliary muscles start to atrophy. So maybe parents, people you've seen, you see them when they start to read something, they'll start to move it further and further away from them to be able to see it clearly. They have hit that point where the ciliary muscles are no longer working right. The lens has lost some of its elasticity, and they lose the ability to focus on things close. That's when you get reading glasses. So overall, these are the parts of the eye. Now what we want to get into is the actual process of seeing. A couple images to show you. Here we have an image of the retina on the left and an eye below it when it is normal, the normal pupil, and when it has been dilated, in an eye exam. So the size of the pupil changes. That retina is pretty darn complex. If we look at it in comparison to a camera, an iPhone 11 camera, 12 megapixel camera, the human eye with all the rods and cones equivalent to 576 megapixels. So technologically, we cannot create anything that is anywhere near what the human eye is. Something to ponder. Now, let's ponder the process of you seeing. So what we're going to get into here is more of what the light is doing. So I'm going to draw a diagram here. Here you are, not to scale. I'll put an eye there in a second. Okay, so let's say you are looking at a tree. Light is going to come from that tree, and I'm not going to draw the actual rays, but light is coming off of that tree and going into your eye. Let's add your eye here. No, it's not going to be to scale. I need a little bit of shape, but you're very happy here. So here is your eyeball, and what the light is going to do is go through the lens cornea system and refract and form an image on your retina. When it forms that image on the retina, I'm drawing in red, that image that forms on the retina, it must be real. You cannot activate the rods and cones if you don't actually have light there, so it must be real. We can tell based on the size of the actual tree and the size of your eye, that image is reduced in size. And it is also inverted. Real we talked about. Let's talk about the inverted. There is an upside down image that forms on your retina, but your eye is not where you see, so then that signal goes to your brain. So from your retina, that signal is going to your brain, and your brain has to interpret that image. Now, if you saw everything upside down, but then with hands and feet felt everything right side up, there would be a sensory conflict in your mind. So then your brain's going to resolve that, and it's going to flip the image over. So then even though the image forms on the retina, reduced and inverted, your brain will actually process that signal, and the brain flips the image over so that you see things right side up. There is evidence that the brain learns to do that somewhere in the early ages, say 1-ish years or younger, that your brain is not flipping the image over, but as soon as it has enough data, it does begin to flip that image over. Exactly what age, not clear. It's hard to get small babies to tell what they can see and what they cannot see. But there have been studies done whereby imagine that you put on, say, special goggles that had lenses and mirrors in them that actually flip the image over. So if you were wearing these glasses, the light coming in from the outside would be upside down, which means that the image on the retina would form right side up, and then the brain would flip it back over. So then wearing these goggles, you would see everything upside down. Well, wearing these goggles continuously for a couple of weeks, the brain was taught to not flip the image over. So then goggles on, the image forms right side up on the retina, the brain does not flip it over, and you see things right side up. So the brain can be taught to not flip the image over. The problem is, if you participate in one of these studies, then when you take the goggles off, then your brain has been taught not to flip the image over, and it continues to not flip the image over. And so then you have to go through a couple more weeks without goggles on of seeing the world upside down and teaching your brain to flip the image over. So there has been some research done to verify that the brain flips the image over, and it is something that is taught. By the same idea, the image on the retina is reduced. Imagine if you saw things much, much smaller than they actually were, you would have some sensory conflict because you would touch things and they would feel larger than you were seeing them. So then your brain also processes so that you see things right side up and you see things as normal life size. So in a very, very simplistic diagram, lacking all relevant size in biology, there's our tree, light going through the lens cornea system, the image forming inverted on the retina, and then the brain flipping that back over. Now let's talk about depth perception. This is an experiment I want you to do. So take a minute, find another person. With another person, I'm going to draw you. I'm going to draw the other person. And I want you to find something that is soft and squishy that you can throw. If you have nothing else, you can crumple up a sheet of paper because it's relatively soft and squishy. So you're going to throw it back and forth to each other. But what I want you to do is cover one of your eyes so that you cannot see. So I'm going to put a patch over one eye. So if you have that pirate mask somewhere around, cover up one eye, have the other person cover up one eye, and then take this crumpled up piece of paper and throw it back and forth. See how well you can throw, see how well you can catch. If it's too hard with each person having an eye patch or a hand over an eye, then have one person with both eyes and one person with one eye closed. Now, sometimes you can adjust and catch, but it's hard to catch consistently because depth perception, how you see and know how far things are away, is based on having two eyes, or what is called binocular vision. Basically, each eye gets information that is slightly different, a slightly different point of view, like in our diagram right here. Again, greatly lacking any relevant biology, but your eye over here on the right side sees a little bit different image, slightly around the right side of the bowling pins. Your eye over here on the left side sees slightly around the left side of the bowling pins. If you went day in, day out seeing double images, you would get lots of headaches. It would be very annoying. So then your brain adjusts and it has to combine those two images. And when it combines those two images, it triangulates and gives you the ability to determine depth, the ability to determine how far things are away. If you only have one eye, you don't have that natural depth perception. Now, you can learn to use other visual cues, but being able to perceive depth with only a single eye, so life of a cyclops, very, very difficult. One eye, you learn to use other visual cues, judging what is in front of things, what is behind, but it is an active mental process if you only have one eye. Two eyes, your brain naturally will triangulate, so it is a passive process. Now, let's consider nearsighted and farsighted. So I have two pictures here. Nearsighted and farsighted, these terms are literally telling you what you can see. So a person that is nearsighted can clearly focus on things that are near. But on the flip side, things that are far away, they're blurry. So when you look at the picture there below, the boy who is close is clearly in focus. The two kids on the sand with the balls are blurry. That person is nearsighted. A person who is farsighted, again, focusing on far, that's what they can see clearly. So that person can clearly focus on far or distant objects. And that's why in the picture below, the two kids tossing the beach ball in the sand are more clearly in focus. But the girl that's in the picture is blurry. Farsighted, you can see things that are far clearly. Nearsighted, you can see things that are near clearly. Now, a little bit of a test. I have no idea how this is going to work over video, so we will see. So I'm going to enlarge my page a little bit, and then I'm going to take this rectangle and I'm going to move it over. What I want you to do is look at this picture, pause the video for a second, look at it, determine who you see, if it's a man or a woman. Look at it if you have contacts or glasses. Look at it with your glasses on. Look at it with your glasses off. Get up from where you are. Look at the picture close. Step back several feet or across the room. Look at your computer screen and see what the image does. So take a minute, pause your video, and do that. Hopefully you made some observations, and maybe those observations varied a little bit based on whether you had glasses on or not, whether you were close or far. This is a simple eye test that was designed by MIT several years ago to be able to do some checking in terms of nearsighted and farsighted. I am going to take our image for a second, and if you watch the image, I'm going to change the size of it. So as I take my image and I make it smaller, you should get to a point where you see a change. When I make it larger, again, you should see a change. There are two images here, an image of Albert Einstein and an image of Marilyn Monroe. And based on your eyes and how you see, you should have seen that image differently or see it change in different locations. So let's talk then about nearsighted and farsighted and what is going on with your eyes to cause this. Here we have a normal eye that is viewing something that is far away. So this is what an eye is supposed to do. When the object is far away, these rays that are coming into the eye are nearly parallel to each other. And so the rays go through the lens and cornea system, and they form an image right back here, clearly focused on the retina. So that's what a normal eye is supposed to do when you are looking at a far object. If you have trouble seeing a far object, which means you are nearsighted, then the problem is the shape of your eye. In this case, if you look at the shape of the eye is too long front to back. The back of the eye should be right there where the green line is referenced to above, but the actual back of the eye is much further away. And so then the light comes in and it goes through the lens cornea system and it focuses to form the image exactly like it's supposed to, but the problem is that the distance to the back of the eye is too big. And so the rays form the image right there where I just put the arrow, but then there's nothing there. So then the rays cross over each other and you get a blurry image that forms back here on the retina. Now, in terms of the distance between the front of the eye and the back of the eye, you're only talking about the eye being too long by fractions of a millimeter. So it's not as large as the diagram shows. So then if we're going to correct for nearsightedness, we have to put a lens in front of the eye that is going to spread those rays apart so that they have to travel a greater distance to come into focus. And that lens, spreading the rays apart, would be a diverging lens. So then correct it. We have the normal eye on the top, nearsighted eye in the middle, and then with glasses or contacts on the bottom, a diverging lens spreads those rays apart. Now, I would emphasize the diagram shows this particular shape of a diverging lens. Yeah, usually your glasses or contacts are not that shape, but they're the shape I'm circling right there. That spreads the rays out. So then it takes them a greater distance to come together, and you get the image forming right there on the back of the eye the way it is supposed to. Now let's consider an eye looking at something that is near. Well, a near object, the rays are coming in from various different angles. The lens and cornea are refracting them so that then you form the image right back here on the retina, exactly like it is supposed to, so that the retina can convert it into an electrical signal and send it to your brain. You can't focus on near objects. If you are farsighted, then it is also a shape of the eye. Your eye is too short front to back. So when the rays go through and they refract in the lens and cornea like they're supposed to, they don't have the distance to come together. D sub I is greater than the distance to the retina. And so they hit the retina and they haven't come into focus. And you see an image that is blurry. Now, we're talking about millimeters here. Fractions of millimeters, so not a distance too great. If we're going to correct for this, then we're going to need to put a converging lens in front. So again, we have all three diagrams here. The normal eye, the farsighted eye, and the farsighted eye with glasses or contacts. That converging lens brings the rays together before they hit the lens cornea system, so that when they do hit the lens cornea system, they're already closer and they don't need the distance to be able to come together. They can come together in a shorter distance and form an image clearly on the retina. So depending on whether if you are nearsighted or farsighted and you have glasses, you can feel the glasses to determine if it's a diverging lens or a converging lens. If it's a converging lens, you must be farsighted. If it's a diverging lens, you must be nearsighted. Contacts also have this variation in shape, but generally they're too thin to be able to feel between your fingers and determine where it is thick and where it is thin. But that's how corrections to vision are done, and it's the shape of the eye that causes those. In terms of your eyes, you're at a reasonably young age, and your eyes might change. You might have a certain prescription one year and then the next year it's different. Well, internally as your body grows, pressures change, and as pressures change on your eye, that changes the shape. And so you may have bad vision and a year later it's better, or a year later it is worse. That'll stabilize somewhere in your late teens, 18, 20, as your body stops growing. Your eye prescription, if you have one, will stabilize. And then the only thing you have to worry about is getting old. And as you get old, everybody becomes a little bit farsighted, and that's the ciliary muscles and the elasticity of the lens that we talked about previously. There are also ways to correct for vision that are not glasses or contacts. Laser surgery, LASIK surgery. In LASIK surgery, let me extend out a little bit. We're just going to leave it there. LASIK, laser assisted, and then a bunch of big words. So basically what they are doing is they are, first of all, carefully mapping the distance between your lens cornea system and the retina. And by that mapping, they can re-sculpt the shape of your lens cornea system. So then once they have mapped it, they slice the outer layer of the cornea. They slide it off, shown right here on the diagram there, and that flap then sits. They use a laser to then be able to re-sculpt the shape. So they are using that laser to be able to pulse, to be able to burn off tissue and remove that tissue to change the curvature, to change the thickness of that lens cornea system so that it is an accurate shape and focal length for the distance between your lens cornea system and your retina. So after LASIK surgery, you can literally see clearly very, very soon. Now, generally, it's good for 10, maybe a little bit more than 10 years. But as you age, things change, shape changes some. So it's not good forever. And it's not good for everybody because it is a process that removes tissue. If you need extra tissue added, you're not a candidate for LASIK. If you've had LASIK once and you try to go back 10, 15 years later to have it again, you might be able to have it or you might not. They remove tissue the first time and there might not be enough tissue there to be able to do it again. Now, the actual biology. We have a picture down here on the bottom of the actual biology. If you don't want to look at the actual biology, then fast forward through this or look to the side. Your actual biology of the process. Boom, right there. There's your biology of the actual surgery taking place. Lots of biology there. Some people are not candidates for LASIK. Here's another variation. Let me bring our images down. My wife, not a candidate for LASIK surgery. She had previously, she doesn't wear these anymore, corneal refractive therapy. And what these are basically hard contact lenses that she would put into her eyes at night before she went to bed. She would put in these hard contact lenses. Being hard, they didn't flex, they didn't change shape. She put them into her eye with this little blue kind of plunger thing that she would plunge and stick to a contact and then shove it in her eye and then release it there. And being hard, it would forcibly change the shape of her lens cornea system. So on the diagram right here, look at the blue lens, and there is a little bit of a gap between that contact and the outer layer of the cornea. The next morning, the cornea will adhere to that lens and it will change shape and fill in those gaps. So my wife would put these in before she went to bed at night. The next morning, she would take them out, and for the next day, she would have better than 20/20 vision. She could go for a day, maybe 2 days, but she generally got in the habit of wearing these every night, and then she would have nearly perfect vision. But they were a little bit on the pricey side, so she does not wear those anymore. But corneal refractive therapy, LASIK surgery, glasses, contacts, those are all different ways to be able to adjust when the shape of your eye doesn't match the focal length of your lens cornea system when you are nearsighted or farsighted. Ponder physics.